Hi, today we're going to be talking about representation learning, which in many ways is very closely related to neural networks. One of the reasons that neural networks have been so successful is that they allow machine learning algorithms to learn representations that are task-specific. And this means that the neural network can decide what features to use, whereas, say, in your feature engineering homework, you had to make that decision. One of the places that deep learning has been very successful is in text and also in images. In both places, deep learning allows us to learn features that are better than what humans have been able to come up based on their own intuitions. And this allows us to answer questions like, how similar is pasta to pizza? And before deep learning, most of the time we either used one-hop representations that said, as a binary feature, is this word pasta or is it pizza, without representing any of the underlying world knowledge that you and I have about these words. And the alternative is to try to use things like knowledge bases, things that have been painstakingly been built over years and years and years, that use a lot of human knowledge and a lot of human effort, but don't necessarily encode things in the right way for an algorithm to be able to use them successfully. But that's not to say that linguists in particular haven't thought about this before. You can know what a word is based on the context that it appears in. And so let's see what this looks like. Let's say you have this sentence. Marco saw a furry little wampum hiding in the tree. And wampum is a made-up word, but you still have a sense of what this word might mean. And that's because there are words around it, like furry little and in a tree. And now you're probably thinking of things like a squirrel that live in a tree. You may even be thinking about a chipmunk, which has the same UK ending as this made-up word, wampum. And this is the kind of information that we can encode if instead of treating each word as a binary, is this word present or absent feature, we represent words in some sort of continuous space. So for example, if we just have a two-dimensional space to represent our words, we can have a set of words that represent technical terms in the bottom left, we can have food in the top left, and then we can have music over here. And so all of these representations are capturing what words appear with each other in similar contexts and thus mean similar things. And the great thing about this is that these features are very versatile. You can use these representations across modalities. You can use these same representations in a text system or in an image system. For example, if you wanted to generate captions based on an image automatically, you could use these same representations to link images and words. They're also a very useful downstream feature. One of the big revolutions in natural language processing is using the features generated from distributed representations learned from large corpora to answer questions like, does this sentence contain a positive or a negative sentiment? No matter what task you're doing, today if you try to write a paper without using these representations as a feature, your paper is likely not going to get accepted. In many ways, this is now the baseline to be using for a natural language processing task. And what we're going to be doing today is learning how these representations can be constructed from data. And we'll talk about how this fits in to the things that we talked about last week from neural networks and multi-layer networks with their hidden units that capture representations of your data automatically. And these vectors that we learn will capture what a word means. And in linguistics, this is often called semantics, so the study of words' meanings. And we'll focus in particular on a model called word-to-vec, which has proved very popular and very useful in natural language processing, although the same insights hold true for many other applications.